We are going to start in a few minutes. Let's wait if anyone else is coming or not. Then we can start with the lecture. Okay, so I guess we can start. So, hello and welcome everyone to the live session of week 11 on the course Experimental Biochemistry, which is being taught by Professor Shagata Dasgupta and Professor Shomodaya of IIT Kharagpur. I am Srijan Sen, and today I am going to take the live session of week 11 lectures which were taught to you, and also discussing with you people a few questions which will help you in solving the assignment and the exam which is coming up for you people. Okay, so I'm sharing my slides with you. I guess my screen is visible to you people. Yes, okay, that's good. So I think I can start. So in today's lecture we would be discussing about something called protein ligand interaction. So previously we have learned, in the previous lectures we learned a lot of things about the amino acid, starting with the amino acids, then the proteins, then the different techniques used for protein purification. After that we learned about the characterization and the isolation of proteins and amino acids. Then we learned about the nucleotides, the techniques related to it, the characterization and isolation of the nucleic acids and all. So in today's lecture, we would be discussing about protein ligand interaction, as to how a protein interacts with the ligand, or what things are related to it, what is the thermodynamics behind it, and how can you actually interpret this protein ligand interaction and find out the different techniques associated with it. So when we speak of protein ligand interaction, there are three types of, or many types of ligands which comes to our mind when we call when we tell about a protein ligand interaction. So basically these ligands can be your small molecules, or which are just your some chemicals and all the small molecules just having very lesser molecular weight and all, and this is interacting with your protein, and this can be certain kind of drugs and all. Also we can speak of protein interactions, where you have one particular protein, say protein 1, which interacts with another kind of protein, which is a protein 2, and then you find the interaction between them. And the third type is your, say, protein nucleic acid interaction, where you're checking the interaction between your protein DNA or a protein RNA. So this type of interactions comes to our mind. So what is about it? So in an conference of some 25th anniversary of the Institute of Molecular Biology at the University of Oregon, Linus Pauling said that the secret of life is molecular recognition, that is, the ability of one molecule to recognize another through weak bonding interactions. So from this comes the concept of binding of ligands to a macromolecule. So from this we can tell that binding is the first step which is necessary for any kind of biological response. Okay, so before any macromolecules can perform a function, they need to interact with some kind of species, say a specific kind of a ligand and all. And in many cases it is seen, like in the case of myoglobin, binding and subsequent release of the ligand might be the sole function of such a particular protein and all. Now, in order to understand the binding, we must consider the equilibrium which is involved between them, as to how the binding is going to get affected by the ligand and the macromolecule concentration, how tightly this macromolecule is binding with the ligand, and how we can experimentally interpret and understand the binding process and the binding data followed by the binding curves and all. So all the characteristic features related to the binding can be understood from the different kinds of factors, like your ligand concentration, the macromolecular concentration, the equilibrium present between them. So these are the different kind of characteristics we can find out from the ligand macromolecule binding process, or the binding phenomenon. Now, reversible binding of ligands is essential. So the specificity of the ligands and the which includes the specificity of the ligands and the binding sites. Now, the ligand binding is coupled, often seen to have coupled to your conformational changes, which sometimes is known as your induced fit model. Whereas in the other case, we speak of the concept of cooperativity, that is, in multi-subunit proteins, the conformational changes in on subunit can affect the others, and these certain interactions can be regulated. Therefore, reversible binding of the ligands becomes very, very essential. Now coming to the interaction with other molecules, that is coming to the reversible, or it is a transient process of chemical equilibrium. So there is an equilibrium between, say, you have a protein, then you have a ligand, say molecule A, molecule B, which remains in equilibrium with your protein ligand, or the entire complex. Now the molecule that binds to the protein is called a ligand, which is typically a small molecule, not always a small molecule though, but can also be another protein or nucleic acids and all. So the region in the protein where the ligand binds is known as the binding site. So where the ligand is coming and binding to your protein, or is attaching to your protein, is called the binding site. Now the ligand binds via some forces are required for the ligand to bind to such kind of a macromolecule, which includes your non-covalent forces, sometimes which includes the hydrogen bonds, van der Waals forces. So there are different forces which are involved in the ligand binding to your protein structure or any kind of macromolecule. So this allows the interactions to be transient. Now, the quantitative description of binding says that if we consider a process in which a ligand, say L, binds reversibly to a site in a protein called P. So you have a protein molecule called P, and then you have a ligand, and this is called the rate constant of association, and this is the dissociation constant. This is the association constant, this is your dissociation constant. Ka stands for association constant, Kd stands for the dissociation constant, and then you're getting is the protein ligand complex. So you can explain the kinetics of such a process where you're via the two kinds of rate constants, in which you have the association rate constant Ka or the dissociation rate constant, which is called the Kd. Then after a particular time point, this process, so in the primary stage you have the protein and the ligand, and after some time the process will reach an equilibrium where there will be equal amounts of all the molecules and the complexes. And then after the process reaches an equilibrium where your association and the dissociation rate becomes equal. So from the constant, the rate constant formula, you can, or the equation, you can write that Ka into the concentration of your protein into the concentration of your ligand is equal to the Kd, which is your into your complex concentration, that is the protein ligand complex concentration. So if you rearrange the equation in different ways, and so the chemical composition can be characterized by the equilibrium constant, where you have the capital Ka, which is your represented by, so here are some of the symbols missing, because this is equals to, and this is multiplied. Okay, so you have Ka, which is equals to your protein ligand complex concentration divided by your protein concentration into your ligand concentration, which is also equals to your Ka by Kd. So the capital Ka, which is your equilibrium constant, equals to your association rate constant divided by dissociation rate constant, which is equals to your complex concentration divided by the individual concentration of the protein and the ligand. Now, if we analyze these binding in the terms of bound fraction, then we can write that we often determine the fractions of the occupied binding sites as and you call the constant called theta. Now, what happens is that this theta is equals to your has a relationship with your equilibrium constant. And this theta equals to your the, as it was mentioned before about the capital Ka, which is equals to your complex concentration divided by your it's not directly related, but it's related to some a part of it, where you write theta equals to your complex concentration divided by the total of your protein concentration. That is, so if you see that your total protein concentration, what is your total protein concentration? A part of it that is present after time, say t, where you have a particular protein concentration plus the protein which is present in the ligand complex formation. So this will total up to give your total protein. So theta equals to the complex concentration divided by your total protein concentration. So that is equals to your theta. Okay, now from the previous equation, if you are substituting this complex concentration with your capital Ka into your ligand concentration and your protein concentration, then what do you get is you get you substitute it and then you rearrange it, and then you get is only the things in terms of your ligand. So now when you are eliminating the protein concentration and rearranging, then you are getting something theta in terms of your equilibrium constant, that is your Ka, and your ligand concentration. So your theta equals to your ligand concentration divided by ligand concentration plus 1 by equilibrium constant. Now, if we express this in the terms of the most commonly used equilibrium dissociation constant, so we have seen that 1 by K or association constant is inversely proportional to your dissociation constant. This is known to us. So 1 by Ka equals to your Kd, so your theta equals to ligand concentration divided by ligand concentration plus your Kd. So this equation is very important for us to keep in mind, because there can be some numericals related to it. Now from just a minute. Sorry for the interruption. So if we plot this theta versus your ligand concentration, that is, if we analyze this graphically, so we see that the fraction of the bound sites depends on the free ligand concentration and your Kd value. Okay, so we have these two. So your this ligand concentration, now if we see that when we do experiments and all, we can see that very less amount of ligand gets actually or gets wants to bind or gets bound to your macromolecule or say your protein. So you can tell that your ligand concentration is very close to your total ligand concentration. So say you have one and then about 10 to the power minus 6 molecules. So you have 10 to the power 6 molecules, and out of that only one or two molecules are actually involved in the binding process. Then that is very close to your total ligand concentration. So that is why we are considering this to be your total ligand concentration. And when we plot it, so the ligand concentration is known, the Kd can be determined graphically or at least via the squares regression, so we do not require it. So the time when it before it gets stabilized or gets into the constant phase, or when your theta is equals to 0.5, that is the time when it is in half of position, and that is the your Kd value. So from this you can actually calculate. So you plot theta versus your total ligand concentration, you get a graph like this, and then you can extrapolate and get your Kd value from your where theta equals to your 0.5. So this is the way of graphically representing the binding stuffs. And in other ways, if you want to plot, or if you want to plot, so we know that P plus L remains is equals to your PL, that is the complex, and your Kd equals to individual concentration of your protein and ligand divided by the complex, which is equals to your total protein concentration minus your protein ligand complex into your ligand concentration, and then by the multiplying by PL and then dividing by the ligand concentration and Kd, we get an equation like this. And when we are plotting your complex concentration divided by ligand concentration versus your protein ligand complex, we get a straight line in the negative with a negative slope, where your slope equals to minus 1 by Kd, and this point represents your complex concentration, which is maximum, divided by Kd, and this is your complex concentration, which is maximum. So if you put all the data in this kind of equation, you get a slope, a negative slope with a straight line. Okay. a straight line with a negative slope, and then you can plot. So possibly you can expect a few questions, like one graph can be this, where you have to ask to plot between theta and L, and you're given four graphs, you have to take the right graph. Or maybe you are given a graph you're asked to plot something like this versus this, and then you are asked what type of curve you can observe, or how can you find the KD from the slope or from the intercept. So y-intercept or x-intercept, and then you have to answer a few questions. So these graphs are very, very important, especially very, very important for your exams and the assignments, obviously. So you can expect a few questions from the graphs. Definitely not the equation though. If not, you are asked to actually write you might expect a few numericals from this equation, along with the graphs are being very important. Now coming to the thermodynamics behind the binding process. Now if you see that the interaction strength can be expressed as your association, which is your binding constant, having the units of molar inverse, whereas your dissociation constant has a unit of molar. That is your 1 by it becomes 1 by m basically. So kd equals to 1 by ka, so that's why it is expressed in terms of molar. And when you speak of interaction, that is the binding free energy, that is del G naught, those have units of kilojoule per mole. So this is important. As to the units are very, very important. You can expect some questions from the units as well, especially about what is the unit for association constant, or what unit can you expect for the dissociation constant. These are very, very important. Now coming to the universal definition of enthalpy and entropy, where del G naught equals to del H naught minus T del S naught, and from there you have got the two equations of Ka and Kd as previously mentioned. Now if you try to relate them, then del G naught equals to your minus RT ln Ka, which is equals to your RT ln Kd, where your RT equals at 25 degrees centigrade is 2.48 kilojoule per mole. And for stronger binding, you should expect a Kd less than 10 nanomolar, and for weaker binding you can expect a Kd of greater than 10 micromolar. So you should know that lower Kd means higher affinity of ligand of the protein for the ligand, and higher Kd value means lower affinity of your protein for the ligand. So this equation is also very important, because there can be a few questions where you're given the value of your Ka or your Kd, and you are asked to find the value of del G naught, or you are asked to comment on the binding affinity and all, where you have to find the Kd value, and then you're asked to comment on its binding affinities. So these equations are very important, the thermodynamic connection related to your binding. These are some of the Kd values of the different proteins and the ligands, and how well or how tightly they bind or weakly they bind. So if we look into the first protein, which is the avidin with the ligand biotin, has a Kd value of 10 to the power minus 15 molar. Then insulin, your human insulin with your receptor with your insulin has a 10 to the power minus 10 molar Kd. Then your anti-HIV immunoglobulin for humans with the GP41, that is your HIV-1 surface protein, has a Kd value of 4 into 10 to the power minus 10 molar. Then you have nickel binding proteins in E. coli with your nickel ion, that is 3 into 10 to the power minus 6, and your calmodulin with your Ca2 plus has 3 into 10 to the power minus 6. Now see, as your Kd value moves towards a lower value, your Kd having a lower value means higher affinity, which you can see for your biotin avidin. Then with an average of or a good binding or a strong binding, you can say, for this is a very tight binding, your biotin avidin. Whereas a good binding can be your for antibody antigen, then your sequence specific protein DNA, your typically receptor ligand interactions, and for the low affinity you can observe for your enzyme substrates and all. So the color bars indicates the range of dissociation constants of the various classes of interactions in the biological systems. You see a few interactions that between the protein avidin and the enzyme cofactor biotin falls outside the normal ranges. The avidin biotin interaction is so tight that it may be considered to be irreversible, that you cannot get back after the complex is formed. You cannot get back to the individual molecules. And the sequence specific protein DNA interactions reflect the proteins that bind to a particular sequence of nucleotides in the DNA, as opposed to the general binding to any DNA site. So these are slide on just commenting on your KD values and the binding affinities. Okay, now coming to the Gibbs energy of binding, I have spoken about it before, that the binding constant or the binding association constant can be connected to the Gibbs energy via this equation G naught equals to RTL and Ka, which is equals to RTL and 1 by Kd, and if you put here a minus, then this value becomes plus. So a binding constant of Ki equals to 10 to the power minus 9 corresponds to a Gibbs energy of 53.4 kilojoule per mole at the body temperature, that is 25 degrees centigrade. And a change in the Ki of one order of magnitude means a change in the Gibbs free energy of 5.9 kilojoule per mole or 1.4 kilocalorie per mole. This is not much important. The equation is only you have to keep in mind. This is about the binding equations and all, where you have the receptor and the ligand, and the same process happens where you have K equals to 1 by Kd, then you have this, and then the enthalpy and the entropy equation, which says del G equals to minus RTL and K, which is equals to del H minus T del S, and minus del G by T equals to del H minus del H by T plus del S. So there are different types of protein ligand interactions which happens, that is the in terms of hydrogen bonds. There are typical hydrogen bonds, then you have untypical hydrogen bonds, and the charge assisted hydrogen bonds. For the ionic interactions, there is the effect of pKa values. Also the local pH of the binding environment will also affect the interaction of your protein and the ligand. The hydrophobic interactions definitely play a role in this, that is the hydrophobic interactions. How are these hydrophobic interactions, or in what manner are they affecting? So they are mainly caused by the displacement, or more correctly put, the liberation of your water molecules from the lipophilic environment to the binding pocket. And some kind of interactions you can observe from the cationic pi interaction. So there is a pi electron cloud, and then you can see some cationic and the electron interaction, because of which it enhances the protein ligand interactions. Okay, so with this we come to the end of the basics of this binding and all. Now we will be speaking about a few techniques by which we can actually understand about the protein ligand interactions. Okay, so the first technique is your isothermal titration calorimetry, or the ITC. So this is the diagram of your ITC. So your ITC is a kind of a direct method. What it does is actually it measures the heat change which is associated with the complex formation at a constant temperature. Now the complete thermodynamic profile of the molecular interaction in a single experiment can be calculated. So what you can calculate? So first thing you need to keep in mind, it measures the heat change. So the heat change is being measured over here. And what other informations can you gather from this experiment is about the enthalpy, then you have the entropy, and from this you can calculate definitely the Gibbs free energy, then comments on the binding affinity and the stoichiometry of binding, as to how many ligands are actually binding with your protein molecule. Is there only one ligand which is binding, or there are several ligands which is binding? In which position they are binding, you cannot tell, but about the stoichiometry of the binding, the information can be gathered from this isothermal titration calorimetry. Now, what do we have in this ITC? We first of all have a syringe, and this gray color thing is your adiabatic jacket. Then you have the sample cell and the reference cell. So the reference cell is for providing the constant power to the reference cell heater, where your del T remains 0. That's why it's an adiabatic jacket, where your change in temperature remains 0. And the power supplied to the sample cell feedback is important to keep the delta T equals to your 0. So this is the entire instrument structure of your ITC. And if you see that after its binding, if you see an endothermic reaction which is occurring, then you will be seeing some of the graphs of mu cal per second versus your time, and you will be seeing some positive lines or in the positive direction, that will be actually increasing with decreasing with your time. So you are seeing that the graph is decreasing with time. In both the cases it's decreasing with time, but if you see that for an endothermic reaction it's in the positive direction, and for your exothermic reaction this is in the negative direction. So these are the two differences, and from here you can actually tell whether your reaction is an endothermic or an exothermic reaction which is occurring after your ligand has bound to your protein with respect to the amount of heat. So as I was speaking, it measures the heat change. So with the change of heat you can actually comment, or from the graph actually you can comment on whether it is an endothermic or an exothermic reaction. Now this is an elaborative view of your ITC, where you have the sensor, then you have the lead screw, okay, and then here is the place where you're injecting your sample, followed by you have a plunger which helps the sample to go in. Then you have the stirring process which goes on. Then you have the syringe. The outer shield is adiabatic, has been an adiabatic environment, and then you have the sample cell, the reference cell, and then you have the inner shield. So this is important. This maintains delta equals to 0. Okay. Now this is a review of free energies, enthalpies, and the entropies of binding. So your del G naught binding equals to your RTL and KD, where your R equals to 1.98 calorie per mole per Kelvin, and your T equals to 273.2 Kelvin, and your RT equals to 0.62 kilocalories per mole at 37 degrees centigrade Celsius. Now if we go with the logarithmic relationship between the free energy and the binding constant, so we need to recall that the del G naught binding is relative to your standard conditions, that is your 1 molar of reactants at 25 degrees centigrade and your standard salt. Now the convenient rule of your thumb is that a tenfold change in the binding constant is equivalent to your 1.4 kilocalorie per mole. That is your delta G naught of A1 minus A2 equals to your RTLN KD of A1 divided by RTLN, that is KD of A2, which is equals to 0.62 kilocalories per mole. The natural log of your 10 to the power minus 8 molar divided by 10 to the power minus 7 molar, which is equals to 1.4 kilocalories per mole. So how many kilocalories per mole change in free energy do you need to change the KD? By 100-fold. So if you calculate it well, you can find out that you are getting an answer of minus 2.8 kilocalories per mole. So it is becoming into 2. because that was 10-fold change. This is won't become your 10 times. Okay, but it is log of your 100, that is your 2 into the value becomes 2 into 1.4, that is the minus 2.8 kilocalories per mole. Now your del G naught equals to your del H naught minus T del S naught, and therefore your minus RTL and Ka, which is equals to your del H naught minus T del S naught. So this is another equation which is important. So when is an interaction called to be strong? So del G must be large and negative. Okay, this is one important point. Your del H naught must be large and negative, that it gains new bonds, and your del S naught must be large and positive. So this is important. Your del H naught, first of all, this equation is important. Now next, coming to your enthalpy and entropy. So del H naught must be largely negative and your del S naught must be largely positive in order to get a large negative value of your del G naught. So del H naught being largely negative means gaining of new bonds, and your del S naught being largely positive means you're gaining of more entropy. Okay, so with this you can actually call an interaction to be strong interaction. Now coming to the next type of your technique, which is your SPR. So this is your instrument or the principle behind your SPR, that is your surface plasmon resonance. So your surface plasmon is the longitudinal charge density wave along the interface of two media, where one is metal and the other is a dielectric one. So you have a metal film over here. Okay, and then there is the liquid or the air, so there is a polarized light source which is striking the metal surface, and then you have a 2D detector array. So these have different components, and this is the angle at which it is striking the metal film. You have a KSP. So this is the Rachman's configuration of SPR, that is the resonance of a surface plasmon is excited at the metal or the air interface, where the angle of incidence of light is such that the evanescent component of your wave factor KEV is equals to your wave vector of the propagating surface plasmon, that is your KSP. So your KEV is proportional to your or equal to your KEV value. So this is a metal surface, and so this is what is your SPR. So the principle behind SPR is that your SPR is excited by a positively polarized light, totally internally reflected light at say glass or a metal film interface. So the surface plasmon is enhancing the evanescent field amplitude, which is your E. Now in the BioCore system, which we use as a sensor chip, now this interface takes the form of an exchangeable gold coated glass slide, and then SPR is observed as a dip in the reflected light intensity at a specific angle of reflection. So you see over here you have a plane polarized light, and it is striking at an angle theta, and then you have the reflected light. Now at this angle you see you have a wave, and then there are different energy functions. You have the KSP and the KX, which is your evanescent field amplitude. Okay, your E is the evanescent field amplitude. So you will see that a linear relationship is being found between your resonance energy and the mass concentration of your biochemically relevant molecules, and when you plot the reflected light intensity versus your angle, you get a curve like this. So it's an inverted cone. So this is the SPR principle. Now the typical SPR signal is like this. You have the light source of your polarized light, it strikes, you get the reflected light, then you have the optical detention. This is say your prism, you have the sensor chip, and these are your antibodies binding to some kind of ligands and all, and when it will bind, so you have so when you plot your intensity versus the angle, you get curves like this. Whereas when you are actually plotting resonance versus time, so these graphs are also important because sometimes you might be asked as to what will be the, you're given four graphs, another same type of questions as before. You're given four graphs and asked to plot for the SPR of intensity versus angle or resonance versus time, and then you have to actually identify this. So first it goes moves in a straight line, and then in the k plus 1 you see it increases, reaches a constant phase, and after a point of time it decreases, that is a k minus 1. Now, what are the different applications of your SPR? So these have different physical applications as well as your biological applications. So among the physical applications, it is used to actually measure. So this is important as to why you would be using this SPR. So for physical applications, it is used for number one, measuring the dielectric properties. The next one being your adsorption processes. Okay, because you are seeing for the antibody and the ligand, so it will also help you to measure the adsorption or make some comments on the adsorption processes. Then the surface degradation or hydration of your say polymer films or the thin organic monolayers or the bilayers. So these are the three important applications of your so these are the three important applications of your SPR. Okay. So first one being it measures the dielectric properties, number two being in adsorption processes, and the third one being the surface degradation or hydration of your inorganic monolayers or the bilayers and the polymer films. For in terms of biological applications, so we use it as biosensors for specific biological interactions, including your adsorption or desorption kinetics, then your antigen antibody binding, and also for epitope mapping for the determination of your say biomolecular structure and interactions of your proteins, DNAs and the viruses. Then you have the lipid bilayers, then you have non-specific biomolecular interactions, that is the biocompatibility, and also it can be used for your tissue engineering. So the first one, what are the applications? It is used as the biosensors. Number two is antigen antibody binding, and the third one is your epitope mapping. For what things? For the first one being your biomolecular structure and interactions, protein, DNA, virus interactions. Then you have the lipid bilayers. Then you have the non-specific biomolecular interactions, that is the biocompatibility, and lastly your tissue engineering. So what are the advantages of your SPR? So it has the ability to perform the real-time measurement, which gives an insight to the dynamic nature of binding system and the layer formation. Then it has usage of selective slides to study the binding events needed to eliminate the need for your labeled reactants. It has exceptional sensitivity, that is small quantities of purified reagents are basically required. So these three advantages are very important. You can perform the real-time measurement for the use for the selective slides to study the binding events, and it is highly sensitive, that is small quantities of your purified reagents are required. Also these surface plasmon resonance has a certain or a few drawbacks. First being it lacks the sensitivity when monitoring your low molecular weight adsorbate. So when you are monitoring your low molecular weight absorbates, then sorry. So in terms of monitoring your low molecular weight adsorbates, it actually lacks that sensitivity, and you can find some discrepancies when you are actually observing it. So this actually is one of the biggest drawback of your SPR. Then there is the rate limiting factor of your mass transport, which can affect your kinetic analysis. And what can we do? So in order to improve the sensitivity, we couple this with your atomic force microscopy, also with your mass spectrometry. So these two methods can be actually coupled with your surface plasmon resonance phenomenon to improve these two disadvantages. One being your it increases when you're actually coupling it, so it improves the sensitivity which you are facing when you are monitoring low molecular weight absorbers, and the other one is the rate limiting factor. So that can also be improved when you use a highly, say, a different kind of measurement technique and all. Okay, now coming to the next technique, which is your IMSA. Okay, let us take 5 minutes of break. After that we can start with the other two processes. So we have two more processes left. One is your IMSA and the other one is your fluorescence anisotropy. So we can discuss it after 5 minutes of break. Okay, so let us restart. Now coming to a different kind of technique, which is your electrophoretic mobility shift assay. So we also call this as the gel shift assay or the gel mobility shift assay, band shift assay, or your gel retardation assay. So in the previous two techniques we were seeing, in the first technique we saw about measuring the heat and all, and in the next technique we were seeing about the different where we are calculating intensity versus your angle and then finding out the interaction. So we have a plane polarized light striking. Now coming to a different kind, which is where we will be using a gel in order to find the interaction between your protein and your ligand. So what we use this technique for, so it is a technique which is used to detect your protein is attached to your DNA or RNA or not. So as we know, there are many cellular processes where a protein needs to interact with the DNA or RNA, like in the transcription or translation, and we can comment on it. So it is actually the technique where we check about your protein and your nucleic acids. It is basically that technique, whether it is binding and all, right? So the first important thing is that it's a protein nucleotide nucleic acid interaction. And so originally it was utilized broadly in the investigation of your sequence specific DNA binding proteins such as your different transcription factors, and it has been in the recent days it has additionally developed to explore the DNA protein interactions, then your RNA protein interactions and all. So this method is a very sensitive method where you use different kinds of radioisotopes to label the nucleic acids and autoradiography. It is possible to use very low concentration and small sample volume. So you do not actually use very high concentration of your DNA and RNA. Even our radio level, small amounts of your nucleic acids is sufficient enough to check the binding of your protein and your nucleic acids. So this is a very important technique and a very sensitive one as well. Right. So what we do, say the purified protein and the cell crude extract are usually incubated with the 32P isotope labeled DNA or your RNA probe, and the complex and the unbound prone P is isolated on the non-denaturing polypropylene gel electrophoresis. So what is the principle behind it? A mobility shift assay is electrophoretic separation of your protein DNA or your protein RNA mixture on a polyacrylamide or agarose gel for a short period, and the speed at which the different molecules moves through the gel is determined by their size, charge, and sometimes your shape. Now how we do and why titration is done. So as we know, we are going to have a DNA which is interacting with your protein, and for that to happen we need to have enough DNA and the protein in the solution. So if you see the second picture first, so there is a shift which has happened. So your DNA bound to your protein, so this is your bare DNA. So you see the concentration also decreasing as the with the increasing DNA forming your protein complex. Now you see is that your DNA is bound to say two proteins, then you will see a shift in the band, whereas your DNA is only binding with your one protein and forming a complex. So this is your bare DNA, and then this is your DNA protein complex. This is your DNA bound to your two proteins. So you see the difference in the bands, and this is the free DNA, which band is also decreasing. So you have DNA, you have your proteins, and when your DNA is interacting with your protein, then you would see that there is not enough of the you have enough of the DNA, but you require actually very small amount of DNA to actually test this kind of to do this kind of experiment and all. Now you have there are different applications of this assay. So firstly, it is used for to study conformational changes in DNA. For example, a IMSA 2D variant with electron microscopy is used for the characterization of the conformation. The next is analysis of cellular extracts for the presence of certain DNA binding proteins, where you have the bound and the free DNA are separated using your EMSA, and it proves useful for stoichiometric analysis, the number of protein that binds per DNA fragment. So it was also used to study whether the transcription factor is attached to the DNA or not, or if the transcription factor is attached, whether it can be targeted or whether it has any kind of activity or not. So with this you can find the different applications of this EMSA. And then there are the different advantages which this assay has. So it can be used with a wide range of nucleic acids, sizes, structure, as well as the wide range of proteins. It is a relatively simple method to perform. It is also used for your qualitative analysis, and it proves useful in the detection of protein that binds to your DNA and cause difficulty in migration of your fragment on the gel. Now it is a highly sensitive method, and usually it usually of low cost. It requires no special kind of equipments, and in this technique it is possible to use both the crude protein extracts and the purified recombinant protein. So a wide, if you see from the first point, so the wide range of nucleic acid sizes and structure, it is a relatively simple method to perform. It is useful in the detection of protein that binds to your DNA, causing difficulty in migration of the fragment, and highly sensitive method, low cost, no special equipments required, and you use both the crude protein extracts and the purified recombinant proteins. The drawbacks is that IMSA does not provide a straightforward measure of the weights of the proteins, as you see that the mobility is influenced by several other methods. So it is not an appropriate method for kinetic studies, and the dissociation is also one of the drawback of your IMSA. It occurs during electrophoresis, thus it prevents the detection, and you see that the interacting biomolecules have different electrophoretic mobilities that also causes difficulties in performing this assay. Now, speaking of a different technique, which is a polarization in a fluorescence experiment. So you have the three components, one which is going to measure your excitation and the other for the detection technique. So the polarization state of your fluorescence can be described by your polarization, which is your P, which is equals to your parallel intensity minus your perpendicular intensity divided by your parallel intensity plus your perpendicular intensity. And when you speak of an anisotropy, where your R equals to your intensity, parallel intensity minus your perpendicular intensity divided by your total intensity. So anisotropy is preferred because it contains the total intensity. So if you see that your anisotropy or your R can be written as your parallel intensity minus your perpendicular intensity divided by your parallel intensity plus your twice of your perpendicular intensity. So parallel intensity plus twice of your perpendicular intensity actually is your total intensity. You can expect a few numericals from this part as well. So if you see from this, so why is the total intensity IT equals to your parallel intensity plus your twice of perpendicular intensity? This is because for the reason of the symmetry, that is the component polarized in the x direction and the y direction have the same intensity of your I perpendicular. But in a given geometry, we detect only one polarized light in the x direction. Now we have to note that the anisotropy of a mixture of fluorophores, that is your Fi, fraction of the ith fluorophore, where your R equals to the summation for I terms of Fi and into your Ri. So that is why you see that the total intensity of IT is equals to your parallel intensity plus the twice of your perpendicular intensity. Now, so what have we have seen so far is we have considered for the frozen molecules. However, in reality, we see that the molecules are much more flexible in a movement and are much more mobile, and the rotation changes the orientation of the dipole theta. Now, the changes in the theta are reducing the anisotropy, which is caused by your photoselection. So we have an equation over here, that is your RT equals to your R naught e to the power minus T by something P, which is your rotational correlation time. That is your device rotational relaxation time, which is the time for a given orientation to rotate through an angle given by the cos e to the power minus anti-cos of 68.42 degrees. So for a spherical molecule, we see that this rotational correlation time being your viscosity into your volume, then by RT, which is equals to 1 by your 6D. That is your, where D is your translational diffusion coefficient. And for a globular protein, you have this rotational correlation time to be your viscosity into your molecular weight, then you have the partial specific volume plus your degree of hydration divided by your RT. So these two equations are also important, along with the general equation which speaks of R for time t equals to your R naught e to the power minus T by rotational correlation time. And for a spherical molecule, we have the rotational correlation time to be this, and for a globular protein, we have the relation time to be this. So these two equations, there might be a few questions where you're given a few of the variables and asked to find the other entities. You can expect. Now we are measuring the fluorescence anisotropy. So this is the vertical excitation you are seeing, and then here you're going to go for the detection in the y direction, and you have an IPA where is your P is the polarizer and the analyzer. IVV equals to your SV into your intensity in the parallel axis, and the IVH in the intensity in the perpendicular one. So the plane which is defined by the direction of excitation and detection is your X and Y, which is called your horizontal. That is, it is considered horizontal in the experiment. Now the measured intensities are identified by two indices which describes the orientation of the excitation polarizer and the analyzer. Now we have to account for the different sensitivities of detection of individual polarizations. Now you have seen that anisotropy equals to your R, which is equals to IVV minus your GIHV divided by IVV plus 2GIVH, where your G equals to SV by SH. So these two equations are another two important equations. Now this is the graph where you're plotting the photon counts divided by the channel, and here you're plotting anisotropy divided by the versus your channel. So this is done for the pop-up molecule. So the scattered light can cause higher anisotropy because it is completely polarized. That is, it is equals to 1. So it is necessary to minimize the scattering for accurate anisotropy measurements. So when there are a lot of scattering and all, then the anisotropy, then you do not get the accurate results. So for that, the scattering has to decrease in order to get your, so the minimum the scattering is, the accurate your anisotropy measurement would be. So for that you have to reduce the scattering to get better anisotropy results. Now you see that the polarization methods are ideally suited to study the aggregation state of your proteins. Now if we consider the case of a protein dimer monomer equilibrium, Now, following either the intrinsic protein fluorescence, which can be possible, or if you are labeling the protein with some kind of probes or some kind of fluorophores, which one would expect that the polarization of the system to decrease upon dissociation of the dimer into monomers, since these smaller monomers will rotate more rapidly than the dimers during the excited state in a lifetime. So this will have lower P, whereas this is going to have your higher P. So hence, for a given probe, the lifetime, the polarization or the anisotropy of the monomer will be less, obviously less than that for a dimer. Okay, so that's all. Now we are going to solve a few questions. So first, you people answer, and then I can actually discuss with you the questions. Okay. Okay, I see no one is over here, so I can actually start discussing with the questions. If anyone comes, then we can actually have a look at it. Okay, so I feel there are no more, there won't be any students, so I can start discussing with the questions. So the first question is, your dissociation constant has a unit of. So I have already mentioned in my slide that your dissociation constant will have a unit of concentration. So for the first one, your option A is right. So if it is your sorry, dissociation constant will be in molar, and your association constant will be in molar minus 1. The next question is, electrophoretic mobility shift assay is a technique for studying DNA protein interactions. It is performed using. So what type of gel we use? So I mentioned it's a denaturing gel. So therefore it is option B, which is your native polyacrylamide gel. The next question is, which of the following experiments can be used to determine the binding kinetics under favorable conditions? So there are four techniques. So all of the four options are correct. The electrophoretic mobility shift assay, IMSA, ITC, then you have the fluorescence anisotropy and the SPR technique. So all of these four techniques can be used to determine the binding kinetics or the protein ligand binding kinetics of. So all these four experiments can be used. Okay, so probably you are late. So I just solved three questions. So I am discussing once more. So the first one was the dissociation constant has the unit of, so as I mentioned, it has a molar. It's calculated in molar, and the association constant in molar -1. So that's by concentration. So for IMSA, we run the native polyacrylamide gel, and to determine the protein ligand binding kinetics at different conditions, we use all of these four techniques. That is IMSA, ITC, fluorescence anisotropy, and the SPR. So let's move on to question number 4. So you can answer them. After that, I might be discussing with you. Okay. So enthalpy of a binding reaction can be determined from. So I discussed this for enthalpy. Which of the following technique do we use? Is it your ITC? Yes. So we use the isothermal titration calorimetry for determining the enthalpy of a binding reaction. The next one, free energy of a binding reaction can be determined from. Okay, right. Okay, I'm increasing. Now is it visible? Okay, tell me. So free energy of a binding reaction can be determined from. A. Okay, and what about the other techniques? So this is an MSQ question. So if you look back to my slides, that all of these techniques can be used to determine the free energy. Be it your fluorescence anisotropy. So there are equations for it. You have the SPR, then you have EMSA. For all of these, will, because from EMSA you can calculate the KD. So when there is KD, so for each of these case, what you are calculating, you are actually finding the binding. So if it is about binding, so say you are calculating the KD or the Ka. So this Ka or KD is related with your free energy or your del G. That's why your all of these techniques will be critical for calculating or can be utilized or used for finding your free energy of any binding reaction. So A, B, C, D, all of these options are correct. Now what does SPR detect? So SPR, surface plasmon resonance, detects change in heat after ligand is added, or the change in the diffractive index of the medium, or the change in the migration of the protein ligand complex, or the change in the viscous drag. Yes. So you say B, that is the change in the refractive index of the medium near the sensor chip. Yes, that is right. So yes, so option B is the correct. Option is correct. Okay, moving to the next set. In fluorescence anisotropy experiment, a small ligand is tagged with fluorescent level. Which of the following is true? This is an MSQ question. So more than one option is correct. So increase in the rotational diffusion of the small molecule is detected. Decrease in the rotational diffusion of the small molecule is detected. The fluorescent level is excited by polarized light. The fluorescent level is excited by the depolarized light. So which of the following is true? In a fluorescence anisotropy experiment, a small ligand is stacked with a fluorescent level. I was just explaining it a few slides before. Yes, option C is correct. So option C is correct, but we actually detect the decrease in the rotational diffusion of small molecules. So this is actually B and C. We do not detect the increase in the rotational diffusion of the small molecule. We detect the decrease in the rotational diffusion of the small molecule, and the fluorescent level is excited by your polarized light. Right? So that is correct. Okay, the next question is: a protein binds a ligand with an association constant Ka equals to 10 to the power 6 molar inverse. What is the most likely measured Kd in the presence of a competing inhibitor? So in the presence of a competing inhibitor, what do you expect the Kd value to be? That would have been the answer if there was no such inhibitor. If there was no inhibitor, it would have been 10 to the power minus 6 molar. That is correct. But what happens when there is an inhibitor present? Does the value increase or decrease? So possibly B is not the right option. 10 to the power 5 molar, that is not right. So 10 to the power minus 6 would have been if there was no inhibitor. So option A or D. So, okay, so when there is a competing inhibitor, you see the Kd value to increase. So, the right answer is your A. And when there is a non-competing inhibitor, you see the Kd value to actually decrease. That is 10 to the power minus 7 you would be observing for a non-competing inhibitor. But for a competing inhibitor, you are getting a Kd value of 10 to the power minus 5 molar. So you need to keep in mind that what happens in the presence of how the presence of an inhibitor actually affects your Kd value. So that is important. You might not be able to tell the actual value if the other variables are not given or the equation has not been discussed with you, but you have to have a general idea of whether it is decreasing or increasing. So 8A is the right answer. Okay, moving to question number 9. What it says, for the from the dissociation, sorry, from the dissociation constant, it is possible to calculate. So what can we calculate from the dissociation constant, or what all we can calculate from the dissociation constant? A and C. Okay. So A and C you say. Anything else you can calculate from the dissociation constant? Anything else you can calculate from the dissociation constant? A and C is right. You can calculate the association constant, which is equals to your 1 by Kd. Also, you can calculate the concentration of the ligand, which is required for your half maximal occupancy of the protein. Anything else? You can, whenever you have a Kd value, you can definitely calculate this. That is your free energy. That is your Gibbs free energy for the binding interaction. So your del G equals to minus RTln Ka, which is equals to RTln Kd. So this is which is you can always calculate. So your A, B, C, all three are the correct options. You got it? Okay, anyways. And why are you so late in the class? It's going to get over very soon. Anyways, you can take part in the question and answer session. That will also help you in clearing up your concepts. So I have discussed a few questions before. I have only a few left. You can definitely participate in that. Okay, coming to the next question is, it's okay, no problem. You can participate in the question and answer session. Okay, that's fine, no problem. So I will be uploading this in YouTube. You can also look back and uh, get back to me in. I don't know how to get back to me, but you can actually write in the comment section if you have any problems and all. I will be uploading this in YouTube, and all of these lectures are actually being uploaded. So even if you are late or not being able to attend the classes, these live sessions, you can actually have a look at it afterwards when you get some time. It's okay, no problem. So you can actually take part in the question and answer session for at present. So the question says, in the titration experiment to determine the dissociation constant, so what is we are looking forward to in a titration experiment to determine the dissociation constant? This is an MSQ question, so more than one option is correct. You say A and B. Okay, so it is, you say the ligand concentration is varied and the protein concentration is kept constant. That is right. The ligand concentration is kept constant and the protein concentration is varied. That is also right. It is necessary to determine the concentration of the free ligand, free protein and the bound complex. No, that is not right. And it is necessary to keep the temperature constant. No. Yes, it is necessary to keep the temperature constant. With a varying temperature constant, the binding might vary. You never know that at high temperature it probably binds. Yes, right. So that's why your A, B, D, all three are correct. Okay, the next question. Question 11, good one. Electrophoretic mobility shift assay is primarily used to study. What do you use EMSA for? This is a very easy question. Yes. So we use it for studying protein DNA, protein RNA interactions. That is, if you generalize it, it's protein nucleic acid interaction. Very good. The next one. A protein ligand complex dissociates with an off rate of 1000. So see, for when we are performing IMSA, we are doing it for say protein nucleic acids. Now when you are doing it for a protein small molecule, so see, if it is a protein protein interaction, then you can do a normal page. But IMSA is a process where you are actually tagging your nucleic acid, and then you are making that interact with your protein. That is the first thing. And then there is the problem of size, then the shape, which also comes into play. The small molecules are very small enough to actually cause an impact on when you're running it in a gel. They are so small that when you might not be able to differentiate between the two bands. So you say that this number of this concentration of small molecule has reacted, but when you're comparing the two lengths, it is not always possible. And for protein protein interaction, there are other techniques which you can use as well. So therefore, for when we are speaking of IMSA, and then we are speaking of only the protein nucleic acid interactions only. Okay. Yes. So the next question is, a protein ligand complex dissociates with an off rate of 1000 second inverse. What is the time constant for this reaction? How many zeros have you put? Yes, right, right. That is option. I think you have put here one extra zero. Okay, coming to the next question. For the protein ligand interaction described above, which experiments is or are suitable to study the kinetics? For protein ligand interaction. Yes, all of these techniques can be used to study the kinetics of protein ligand interactions. Yes, that is right. Okay. Next question is ligand A and B binds the protein P with a dissociation constant of 1 nanomolar and 100 nanomolar. Which of the following is true? A binds P more tightly, B binds P more tightly, A has faster off rate, or B has faster off rate. Yes, that is correct, because A binds P more tightly because it has lower Kd value, and lower Kd value means tighter binding. Yes, that is right. Okay. Next question. Question number 16. Ligand A and B binds a protein with a dissociation constant of that is K of 0.001 second inverse and 0.1 second inverse. For A and B, association constant rates K on are 10 to the power 4 mole inverse second inverse and 10 to the power 7 mole inverse second inverse. Which of the following is true? So see, your so if you see the K off, that is your dissociation rate constant for your protein binding with your ligand A, and one has a high Kd value and one has low association value. Yes, I'm telling. So see, so when you are seeing that for A and P, you have the dissociation rate constant, that is the K of, which is your 10 to the power minus 3 second inverse. And for your PB, it is 0.1 second inverse. Okay. And when you are checking the association rate constant, that is your K on, it is 10 to the power 4. And for PB, it is your 10 to the power 7. So from this, you can actually tell that one thing, that your B binds P more tightly from the second thing, that your B is binding P more tightly, that's why it's having a association rate constant of your 10 to the power 7. This you can tell because it is having higher association rate constant value. The other thing which you can tell from the first statement is the K of value, that is your 0.001 second inverse and 0.1 second inverse. You can tell that is your AP complex is longer lived than your BP complex. So here you can comment on the longevity of the two complexes. So the lower your K of value is, the higher is your complex going to live. That is simple. So from the association constant value, you can tell about the tighter binding. You can comment on the binding. So from this you can tell that binds P more tightly. Whereas from the K of value, which is given in your second inverse, then you can tell that because for the P and A, the K of value is low, and for P and B, the K of value is high. So the lower K of value is indicating that that complex is going to live longer and it's going to dissociate slower. So dissociation slower means longer the complex is going to stay. So that's why B binds P more tightly, that is true, but your AP complex is going to live longer than your BP complex. And these are the questions which you can definitely expect in your exams. This can trick your minds, but you have to answer them very smartly. So two of the options are correct. One is your B and one. In the previous question, we could not comment on the K on and the K of values, because you see in the previous question, it is the dissociation constant values which are given. These are the dissociation constant values, and you see here it is being expressed in terms of time. So it's about the time, it's second inverse. You see the units over here. This is in where is it? So in this case it was in molar, so it is a dissociation constant value, and here we are speaking of the time. So see, this is a off rate. Okay, so this is the rate of, here the time is involved, so here we can comment. So when you are seeing that the units is given in second or second inverse, so here we can comment on the longevity. But when it is given in terms of your say molar, then it is speaking of the dissociation rate constant. So you have to also observe the units before you are making any comment. So previously we could not make any comments on the K on and the K off, because the units were given in molar, and we can comment it only on specifically on the rate constant values. Okay, but here we can comment because here that second inverse is given, where the time factor also plays a role in this dissociation and the association rate thing. Did you get it?
Okay, sir, yes, got it.
Okay, that's good. Okay, coming to the next question. I think that's the last question. Yes. So the dissociation rate constant for a protein DNA interaction is determined by EMSA. The intensity of the free ligand can be fit to which of the following equations to obtain the K off? So this equation you just have to keep in mind. I haven't discussed this equation. If you know, you can tell. Otherwise, this is, I can tell you the equation. Okay, someone says B. So as I have not discussed it, I won't be telling anything. So the right answer is actually A. So when you are calculating the K off, it is equal. It is I equals to I naught 1 minus e to the power minus K of into T. So just keep this equation in mind. That's why I'm not supposed to put this as a question, but this question was there in the previous years. That's why I put up this. So keep this equation in mind, that I equals to I naught 1 minus e to the power minus K of into T. So that is the equation of calculating your K off. Okay. Mm, okay. I will then update my at present I don't have the derivation, but okay, I will then update my slide and put it up. You can get that from the NPTEL team. Okay, I will do that. Okay, that's all then. Thank you.
Hello.
Yes, tell.
Uh, Sir, actually, I had two doubts. If you don't mind, can I
Yes, yes,
ask,
yes, sure,
please?
sure, tell.
Okay. Uh, Sir, can I share my screen?
Yes, yes, sure. Wait, I'm then unsure.
Okay. Is my screen visible?
Yes, yes, it's visible. Tell me.
Oh, okay. I was just confused with this numbering of this purine. Like, we can also number it this way, no? Uh, the one which I have marked in blue color.
Yes. Can you please
But
can you please enlarge it?
uh, okay, I don't know.
Okay, no
It is
problem.
not.
Okay, I'm seeing. Okay, I'm trying. So, what is your problem over here? Means
So
you can
they have
number it.
named from this nitrogen, what they have named, but I wanted it to name from the bottom nitrogen, where it is marked, they have marked it as 3, but we can also mark that as 1, because then also the other nitrogen will get the lowest number, and the other side of the bond which has pi and 4, that also will get the lower numbering only. So why they have named like this?
So, so you see it from how do you see it from that 7 and 9 when you're numbering it in this pattern like 1 2 3 like where you have numbered, is it coming 7 and 9 in that particular fashion only?
Yes, see, sir, if you go through like this, the blue color, then it is like that only 1, 2, 3, 4, 5, 6, and 7, 8, 9.
And I need to actually check. Okay, because you see.
I tried to search Google it, but I don't know. I did not found any explanation.
Okay, I need to also then look into it because I also haven't thought of it much.
Yeah, I also just got this. I don't know how I got this doubt, but now I have it. Okay, no worries. I will keep this in the discussion forum.
Yes, yes, yes. So there I can might be able to answer you. Okay, I will get right answer over there. After I will.
Okay, so I just have one last doubt. Like they name three you this is there. I hope it visible.
Yes, yes, yes. Tell.
So they name this five prime, no? This five prime where phosphate group is attached, and now here the below is three, three because at three prime the phosphate group is attached. So
Yes.
again, with this nomenclature, I wanted the rules that how they are naming this 5 prime, 3 prime on basis of phosphate only.
See, first of all is that the five prime. So why the three prime? Because your phosphate is attached to the three prime hydroxyl group.
Right,
Yes. So yes, just as Amardeep is telling, it is on the basis of the carbon. Okay, not on the basis of the phosphate.
sorry, can you repeat?
It is on the basis of the carbon chain or the
Right,
carbon number, right? So
right.
when the phosphate is attaching to your 3 prime, so what will happen the next when the nucleotide is going to attach, it is going to attach to the oxygen which is attached to your phosphate group. So this oxygen is a part of the CH2OH group, which is a part of the 5 prime. So 5 prime where you have the CH2OH. So one H is replaced by the phosphate group,
Yes.
and when you have the 3 prime OH, so one H is replaced by the phosphate group, and then the next nucleotide is attached via the 5 prime end.
It won't be attached to 3 prime because at 3 prime the phosphate is there, because where the phosphate is
No,
there, there
the
it
3
will.
prime phosphate is attaching to the 5 prime. It's not the
Okay,
3
so
prime, it's not the, it's the 3 prime OH where the H is replaced by the phosphate, and then the 5, that particular phosphates, another oxygen is actually attaching to that CH2 5 prime group.
I did not got you. Okay, this
You
sir,
take this,
you are
this,
explaining this one, no?
yes.
Okay,
So
so
you are seeing
I
the CH2, you are seeing the CH2 group of the first A.
right,
So that is the 5 prime end, because that is the 5
right.
prime. Okay, and to that you have the phosphate group attached. So that is the
Yes.
N terminus. That is the N terminus. You look at the next one. So then
Yes,
at the
yes,
3,
okay, yes. So that 5 prime is going to attach with the 3 prime of
yes,
above
yes,
residue.
yes,
Yes, yes, okay, okay, got it. Okay. And the acidity of this nucleotide is only because of this
yes, of this
phosphate group.
phosphate group.
Okay, 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 got it. Okay, sir, thank you.
Okay. So you can put up the questions in the discussion forum if you face any time in the while studying.
Okay, sir, and sir, just if I have really important doubt, not like the general doubt, then can I get the email ID or
Yes, yes, I'm
anything?
writing the email ID. You can get back to me.
Okay, okay,
Yes,
sir,
yes.
thank you so much.
Okay, no problem. Okay, good day. Thank you.
Okay, have a good day.